According to the 2002 National Electrical Code, specifically Section 408.4, it is not permissible to directly feed a 120/240 volt single-phase subpanel from a 120/208 volts three-phase 4-wire panel without the use of a step-up transformer. The primary reason for this requirement lies in a voltage difference between the source and the intended load. The 120/208 volt system is a three-phase system derived from a Y connection, with the voltage between any two phases is 208 volts, and the voltage from any phase to neutral is 120 volts. On the other hand, the 120/240 volt system is a single-phase system typically derived from a center-tap transformer, where the voltage between the two hot legs is 240 volts, and the voltage from either hot leg to neutral is 120 volts. Feeding a 120/240 volt subpanel directly from a 120/208 volt source would result in an undervoltage condition for any loads designed to operate at 240 volts. These loads would receive only 208 volts, which could lead to inefficient operation, overheating, or even damage to the equipment. Furthermore, the nameplate voltage rating on the subpanel is crucial for future reference and safety. If the subpanel is labeled as 120/240 volts, it implies that it is designed and intended to be supplied with that voltage. Connecting it to a 120/208 volt source would create a mismatch between the indicated voltage and the actual voltage, potentially causing confusion and hazards for anyone working on the electrical system in the future. To ensure compliance with the NEC and to provide the correct voltage to the 120/240 volt subpanel, a step-up transformer is necessary. The transformer will convert the 120/208 volts three-phase power to 120/240 volt single-phase power. The selection of the appropriate transformer size and type is crucial to ensure that it can handle the load requirements of the subpanel. Factors to consider include the total amperage of the subpanel, the type of loads connected to it, and any potential for future expansion. The transformer should be installed in accordance with all applicable codes and regulations, including proper grounding, overcurrent protection, and ventilation. It is also important to ensure that the transformer is properly labeled with its input and output voltages and current ratings. In addition to the step-up transformer, it may also be necessary to install additional overcurrent protection devices, such as circuit breakers or fuses, to protect the transformer and the subpanel from overloads and short circuits. These devices should be sized according to the transformers and the subpanel's ampacity ratings. It is also important to ensure that all wiring and connections are properly sized and installed to prevent voltage drop and overheating. The use of appropriately sized conductors and properly torqued connections is crucial for ensuring a safe and reliable electrical system. Furthermore, grounding is essential for the safety of any electrical system. The grounding system should be installed in accordance with the NEC and should provide a low impedance path for fault currents to return to the source. This helps to ensure that overcurrent protection devices will trip quickly in the event of a ground fault, preventing electrical shock and fire hazards. The grounding system should include a grounding electrode, such as a ground rod or a metal water pipe, and a grounding conductor that connects the equipment grounding terminals to the grounding electrode. In summary, feeding a 120/240 volt subpanel from a 120/208 volts three-phase panel is not permissible without a step-up transformer, according to Section 408.4 of the 2002 NEC. The transformer is necessary to convert the voltage to the correct level and to ensure that the subpanel receives the voltage it is designed to operate on. Proper installation and sizing of the transformer, overcurrent protection devices, wiring, and grounding system are crucial for ensuring a safe and reliable electrical system. Always consult with a qualified electrician or electrical engineer to ensure compliance with all applicable codes and regulations. Additionally, consider the following points. Firstly, understanding the implications of voltage mismatch. Connecting a 120/240 volts rated device to a 120/208 volts supply will result in the device receiving approximately 86.7% of its intended voltage, calculated as 208 volts divided by 240 volts. This undervoltage can lead to various problems, including reduced performance, increased current draw, and potential overheating. For example, motors may run slower and hotter, potentially shortening their lifespan. Heating elements may produce less heat, and electronic devices may malfunction or fail to operate correctly. Secondly, considering the impact on different types of loads. Resistive loads such as heating elements and incandescent lights will experience a reduction in power output proportional to the square of the voltage ratio. In this case, the power output would be approximately 75% of the rated power, calculated as 0.867 squared. Inductive loads such as motors and transformers are more sensitive to voltage variations. Undervoltage can cause motors to draw excessive current, leading to overheating and potential damage. Electronic loads such as computers and appliances with electronic controls may malfunction or shut down due to the undervoltage. Thirdly, the role of a step-up transformer. The primary function of a step-up transformer is to increase the voltage from a lower level to a higher level. In this scenario, the transformer would take the 120/208 volts three-phase input and convert it to a 120/240 volts single-phase output. The transformer must be properly sized to handle the load requirements of the subpanel. The kVA rating of the transformer should be equal to or greater than the total kVA load of the subpanel. Fourthly, regarding transformer selection criteria, when selecting a step-up transformer, consider the following factors. Input voltage. The transformer must be designed to accept the 120/208 volts three-phase input voltage. Output voltage. The transformer must provide the desired 120/240 volts single-phase output voltage. kVA rating. The transformer's kVA rating must be sufficient to handle the total load of the subpanel. Efficiency. Choose a transformer with high efficiency to minimize energy losses and reduce operating costs. Impedance. The transformer's impedance should be appropriate for the application to ensure proper voltage regulation and fault current protection. Fifthly, paying attention to wiring and overcurrent protection. The wiring from the 120/208 volts panel to the transformer and from the transformer to the 120/240 volt subpanel must be properly sized to carry the expected current. Use appropriately sized conductors and ensure that all connections are tight and secure. Overcurrent protection devices such as circuit breakers or fuses must be installed to protect the transformer and the subpanel from overloads and short circuits. The overcurrent protection devices should be sized according to the transformers and the subpanel's ampacity ratings. Sixthly, grounding and bonding are extremely important. Proper grounding and bonding are essential for safety. The transformer and the subpanel must be properly grounded to provide a low impedance path for fault currents to return to the source. This helps to prevent electrical shock and fire hazards. The grounding system should comply with all applicable codes and regulations. Seventhly, National Electrical Code requirements. Section 408.4 of the National Electrical Code requires the use of a step-up transformer when supplying a 120/240 volt single-phase load from a 120/208 volts three-phase source. Other sections of the NEC may also apply, depending on the specific installation. Consult the NEC for complete requirements. Eighthly, labeling. The 120/240 volt subpanel must be properly labeled to indicate the voltage and amperage ratings. The label should be clear and easy to read. This helps to prevent confusion and ensures that the subpanel is used correctly. Ninthly, professional consultation. It is always recommended to consult with a qualified electrician or electrical engineer before making any electrical modifications or installations. A professional can help to ensure that the installation complies with all applicable codes and regulations and that it is safe and reliable. Tenthly, addressing the nameplate inaccuracy issue. The nameplate on the subpanel should accurately reflect the voltage that the subpanel is designed to operate on. If the subpanel is labeled as 120/240 volts, it should not be connected to a 120/208 volt source without a step-up transformer. Connecting it to a 120/208 volt source would create a mismatch between the indicated voltage and the actual voltage, potentially causing confusion and hazards. It is always best to use a subpanel that is specifically designed for the voltage that will be supplied to it. If this is not possible, a step-up transformer must be used to ensure that the subpanel receives the correct voltage. In addition, always ensure that all electrical work is performed by a qualified electrician and complies with all applicable codes and regulations. This will help to ensure the safety and reliability of the electrical system. And lastly, to summarize the considerations, remember voltage matching, which is extremely important for safe and efficient operation of electrical equipment. Use of a step-up transformer is mandatory to convert 120/208 volts 3-phase to 120/240 volts single-phase. Proper sizing of conductors, overcurrent protection, and grounding are crucial for safety. Always consult a qualified electrician to ensure code compliance and safe installation practices. Following these guidelines will help to ensure a safe and reliable electrical system.